All right, guys, we're going to start chapter 3, circular motion. Now, this is 3.4 actually section. We're going to have circular motion as parts of chapters 3 and 5. And we skipped those parts when we were in those chapters just because it makes the most sense to kind of do them together, I think. So, going back, we're going to focus on like the velocity and acceleration parts of motion in a circle in chapter 3. Although we're going to discuss some force aspects today, there won't be anything mathematically with forces until we move into the parts in chapter 5 later in the week. All right, so we're going to specifically focus on uniform circular motion. And I'm going to use an example of a ladybug walking in a circle to describe what that means. Uniform circular motion is when something travels in a circle at a constant speed. So we can see this ladybug goes around traveling at a pretty steady pace, right? There's a reason, though, we can't say that something travels at uniform circular motion at constant velocity. And it comes back to something we learned about velocity in the past. Velocity cannot be constant in a circle. Even if the speed is constant, velocity always is changing direction. Therefore, it's changing the vector, not by speeding up or slowing down, but by changing its direction since it's a vector quantity. Which brings us into now finally talking about the third or special type of acceleration. Remember, up to this point, all acceleration we've dealt with has either been speeding up or slowing down acceleration. Well, now we focus on what we call centripetal acceleration, which is acceleration due to changing direction. All right, because the definition of acceleration is change in velocity over time. Well, there's three ways to change velocity: speed up, slow down. Those are both by changing magnitude, and change direction. We learned that in the past. So we give it a special name. We call it centripetal acceleration, spelled like this. But your book more often uses the term radial acceleration. It means the same thing. I usually use centripetal. That's what I'm used to. All right, and centripetal means towards the center. That's exactly where it points. So if we show both vectors, velocity and acceleration on this, that acceleration points towards the center, and we'll get to more why in a second. Okay, that's where the force discussion comes in. But the main thing right now is if something is in uniform circular motion, that means it's not speeding up or slowing down, constant speed, but we can't say constant velocity because the velocity vector is always changing direction. And notice velocity vector points, it does constantly change in direction, but it always points in the same fashion as far as the circle goes. It points tangent to the circle. And if you remember that term from geometry, tangent to the circle, a tangent line to a circle, is a line that touches the circle only one spot and is perpendicular to the radius. So sometimes we'll refer to this velocity as the tangential velocity. All right. Now, it's not that the ladybug or something traveling a circle can't speed up and slow down. It's just that usually when we first study circular motion, we study it in a uniform fashion because this is the simplest way, basically. All right, we could have this ladybug speed up and slow down, and then we'd have a secondary acceleration. If you're going in a circle or a partial circle, you always have the centripetal acceleration pointing inward. If we were speeding up or slowing down as well, we would have a tangential acceleration due to that speeding up and slowing down. But for uniform circular motion, the only acceleration is inward. Somewhere later, you will have some problems with both types of acceleration, and we'll take care of that then. For now, and later in the notes, we'll discuss that a little bit more. But for now, this section of this chapter focuses on the uniform circular motion, meaning we're at constant speed. The velocity vector, notice its length does not change because like all vectors, the length of the velocity vector is relative to its magnitude or how fast it's going. All right, so that's just some basics to start of this idea. And next we'll talk about what causes something to go in a circle. Because Newton's laws, which we discussed, especially his first law, states that an object moving at constant velocity will stay at constant velocity unless acted upon by an unbalanced force. But remember, this object, or any object in circular motion, is not moving at constant velocity, because the velocity is constantly changing direction, right? So that must mean there's some unbalanced force holding this ladybug on. All right? Or in other words, let's put it this way. Things can't magically go in a circle. We said in the past with linear motion, things can't magically speed up or slow down. What has to cause it? A force, right? Because things want to just stay steady, what they're doing, right? So this ladybug, at any given moment, really wants to just go the direction of the velocity. But there's something that's making it go in a circle, right? And that something, in case of the ladybug, would be friction, all right? But that friction would be known more generally as a centripetal force. A centripetal force is any force that causes circular motion. So it might be friction. A car rounding a turn is friction. Friction is the specific force that's causing it to go in a circle, and it is centripetal. Now, friction is not always centripetal. Be careful with that. We're saying in the right conditions, if that's what's making something go in a circle, then it's centripetal. So the term centripetal or radial force is a general term, like a category of forces. Any force or forces that make something go in a circle. If you put something on a string or a rope or something like that and swing it around, then what's making it go in a circle is tension. All right, tension is not always centripetal. If I just hang something from the ceiling on a string and it's not going in a circle, tension is not centripetal. So we're just saying in the right conditions, it could be a centripetal force. A roller coaster going through a loop. The track is pushing back on the coaster, making it go through a loop. That's a normal force that in that condition is centripetal. All right, and centripetal means towards the center, also known as radial. We could also use, and we will later in the week, Newton's second law. We just adjust it. We know that the sum of all forces equals ma, right? Well, this is just the centripetal force or forces equal m times the centripetal acceleration. We could use this specific for that. In most cases, there's going to be only one force causing something to go in a circle, but there could be multiple ones. There could be, and we'll get to those as well. But the most common forces that make something go in a circle are friction, tension, normal, and gravity. Gravity, especially when we're going in orbits, and that's going to be focused on in a later chapter. All right. One big misconception that we got to be careful with is the fact that it sure feels like there's an outward force. All right. I can't change this simulation from being a ladybug, but let's pretend it's a car. And we're all passengers in this car. And we should all know from experience, when a car rounds a turn, especially if that car is going pretty fast and it's a sharp turn, the passengers inside may feel like they sway to the outside of the turn. So if this ladybug was a car and we were all in it, we might sway towards the outside, which is towards our right, in this case, based on the direction the ladybug is going, to the outside of the turn. And you might think, well, geez, that feels like a force, right? And it sure does, but it's not. And here's where you get careful. The only force is the force inward. In the case of a car around the turn, that's friction, okay? That outward feeling of a force, which is not a force, is the effects of inertia. We learned that term before. And inertia is the tendency for an object to want to keep doing what it's doing. Remember, every given moment, the velocity vector is changing direction. It's always tangent, but tangent to the circle, when the object changes position, is always in a different direction, right? And that means at any given moment, this ladybug wants to fly off. All right? If this is a car around the turn, and all of a sudden the turn became a sheet of ice where there was almost no friction, the car would fly off tangent to that path. It would just fly off in a straight line. All right? Once the force that is making you go in a circle, the centripetal force, releases you, you fly off tangent, as long as there's no other significant forces acting on you, in a straight line tangent. And the fact that you want to fly off at any given moment and some force is not letting you, some inward centripetal force giving you a centripetal acceleration inward is not letting you, makes it feel like there's an outward force on you, that interaction between inertia and that inward force. But there really isn't. Some of us may have been on an amusement park ride kind of like this one. We'll play a short video of it. I'm not going to play the whole thing. But this is a common ride in a lot of amusement parks. There's a similar one in Idlewild, where these people, and by the way, these people have this little tiny chain strap right here, which FYI does nothing. If there's something wrong with this ride, that chain is going to provide no safety. That just provides a feeling like they did something to hold you in. What provides you the safety is the motion you are in this ride. In a ride like this, doesn't raise right away. As this thing gets going, I'll fast forward a little bit. This ride slowly accelerates, speeds up, a regular acceleration, to some determined max speed that gives these people a great enough velocity that the inertia effects are high enough that they really want to fly off. All right? So if these, relating it to the ladybug thing we had here, right? This looks like it's rotating to the right. So each one of these people have a velocity vector tangent to the circle that they're in, the circular cylindrical container they're in, to their rights, pointing tangent. The centripetal acceleration is inward. And what's making them go in a circle right now is the normal force of the back of this pad they're up against, pushing on them towards the center. So this centripetal force is a normal force. And once they go fast enough, fast forward a little bit, this ride starts to raise up almost vertical, not quite, but almost. And because their inertial effects are great enough due to the high speed that initially the ride accelerated to, they will stay even in a vertical position against that wall. If this was going too slow, they're in trouble, because then their inertial effects aren't that great, and the push of the wall and the fact that they want to fly off won't interact together in such a way that holds them on. But to these people, it sure feels like they are undergoing an outward force, but it is not. Even if you rode a ride like this and you try to push your body forward, it pulls back. But really that feeling is your inertia, the fact that you want to fly off this ride. And the fact that that velocity vector is always tangent. You want to fly off, the pad on the back of you in that ride is not letting you. The only force is inward towards the center of the circle. There's also some variations of this ride where it doesn't lift you up, where it spins you in a circle and the floor drops out from you. We will eventually do a problem on a ride like that, because friction, vertical friction comes into play on the ride like that. So we'll see a variation of this ride sometime in the next part of this lesson later in the week. All right, so going back and just recapping the most important things right now. When something's going in uniform circular motion, it is not speeding up or slowing down. It's a constant speed, but changing velocity, because the velocity vector always points differently, causing an inward acceleration that is centripetal, and a force causes that. There's got to be a force making you go in a circle that causes the centripetal acceleration, and the most common forces are friction, normal, tension, gravity, as far as anything centripetal. Centripetal means towards the center. Another name for it is radial. So remembering all of that, let's move forward with the notes and look at some equations. The first equation really comes from V equals D over T, which we got to be careful about some things we learned about that in the past. If you recall, when you use the formula V equals D over T, if we know the object was traveling at a constant speed, then we know when we use this formula that we find not just any old velocity, that would be an instantaneous velocity at any given moment. So if something's undergoing uniform circular motion, remember that means speed is constant. So that does mean if we use a formula like v equals d over t, then that means it's not only it's better than an average, it's instantaneous. So we need to tweak this though, because d is actually going to be the circumference of the circle. From geometry, you should know that the circumference of a circle is the outer path. So if we if we took this path and straightened it out, that would be the d of it, all right, in this formula. And circumference is 2 pi times the radius, or pi times diameter would be another way to say it. And we divide it not by any old t. In this formula, we have little t, and that was just any old time from point A to point B when we used it linearly. But big T is what we replace in it now. And big T is a more specific time. It's called the time period. It's a time period is the time it takes for some kind of cycle kind of motion. And a circular motion is a type of cyclical motion because it repeats itself. So if we timed how long it took the ladybug to go around one full revolution, then that would be the time period. So our v equals d over t for UCM is actually 2 pi r over big T. That's where it comes from. And sometimes we call this the tangential velocity because it always points tangent to the path like we said earlier. Now for centripetal acceleration, the main formula is a sub c equals v squared over r. This formula will prove hopefully in an in-person lab when we all get back together. So for now, just take my word for this formula. And if AC equals v squared over radius r, we could plug in this formula, sub it in for the v, square it, and clean it up algebraically, and we get a secondary formula for centripetal acceleration. Now here's where we got to be careful. Remember, right now we're mainly dealing with uniform circular motion. That means constant speed. However, there will be times in the future where we deal with circular motion where the object is speeding up and slowing down and moving in a circle. In that case, we got to be very careful because just as in the past with linear v equals d over t, if we are not at a constant speed, then this formula at best is an average. Okay? And if this formula at best is an average, if we're not at constant speed, and this formula was used to make this formula, then we also have that problem. At best, this would be an average centripetal acceleration. However, this centripetal acceleration formula right here is good for any given moment, assuming the v is good for that moment. So if we plugged in an instantaneous velocity, if the instantaneous velocity was 16 meters per second and plugged it in here, that would be at that moment's instantaneous centripetal acceleration. But since this version of the formula is based on essentially v equals d over t, and if we're not constant speed, then this formula and this version of the AC formula are only good for UCM. Okay, we'll stress that again when we come to a situation where that applies. But if we're definitely in UCM conditions, uniform circular motion, constant speed, not speeding up or slowing down around the circular path, then we don't got to worry about this. They're all good. All right, so with those in mind, also units-wise, although centripetal or radial acceleration is a special acceleration due to changing direction, its units are still what we normally want it in, meters per second squared. V is we want in meters per second. R, radius, we want in meters. T, time, big T, time period, seconds. Convert if they're not. All right, the examples in this chapter are very easy once you know the formula. So I'm going to let you guys go ahead and take a look at them on your own. They're on pages 84 and 85. Basically, if you pick out the givens and match the right formula, it's a plug and chug, nothing tricky. So please look over those on your own. It'll only take you a moment to follow those. Now, I do have a few notes here for non-uniform circular motion. That's when we don't have constant speed. I already just a moment ago mentioned some of that. Non-uniform circular motion is when speed is changing around the circle. If we have that, which again I can't do on this simulation, however, if we did, this velocity vector's length, it would still point tangent, but it would be changing at every given moment. The length of this vector would be changing if we were speeding up and slowing down or this ladybug was. And that would cause a tangential acceleration also that would point tangent due to the speeding up and slowing down. But again, in UCM, the acceleration is only inward towards the center. And the reason why the acceleration is towards the center, the centripetal acceleration, is because if the force is towards the center, we learned in the past with Newton's second law that if the overall direction of the net force will also be the direction of the acceleration. So if that's force is inward, the acceleration is inward. All right. So if we do have non-uniform circular motion, though, then really the only formula that's really good is AC equals V squared over R for the given V at any moment. Okay, and we could even bring back in old calculus concepts. For this tangential acceleration, this is the one for speeding up or slowing down, not centripetal. Okay, be careful, that's tangential. That's if we have speeding up or slowing down. It would equal the first derivative of a v of t, v tangential of time function. Just like in the past, acceleration would equal the first derivative of a regular linear velocity. But that's for tangential, not centripetal. So it says here we will not be doing problems of this type. We won't right now. All right? Later on down the road, we might get some problems with both tangential and centripetal acceleration. But for now, just worry about just a straight up constant speed uniform circular motion. All right, so that's pretty much all there is to the circular motion out of section 3.4. I'm going to post a homework set, which like always is still not going to be due to the test, which won't be till mid to late next week. Okay, and we'll figure out as we go how you guys are going to turn in that homework, since I won't be seeing you for who knows how long. But just get them done. Begin these problems, and tomorrow we'll go on to the chapter 5 portions of including forces in the problems.